Recording.
Okay. Hello, everybody. Good afternoon, good evening, everyone. It's my great pleasure to introduce Professor Piermarco Cannarsa from Università di Roma Tor Vergata in Rome, Italy. And Professor Piermarco is a full professor there in the University of Roma Tor Vergata. He is an expert in control and also in Hamilton-Jacob equations. And today he's going to talk about a reconstruction of degeneracy region for a class of parabolic equation. So Piermarco, thank you very much for accepting our invitation to deliver again a talk in our seminar. It's a great honor to receive you again here. So you have the word.
Thank you for the introduction, Diego, and it is my great pleasure and honor to be able to speak at this conference in celebration of the first 100 talks of your seminar. I'm very interested and connected with the research of Brazilian mathematicians, and I think we have a lot of interests in common, and a lot of activities has passed and is to be expected for the future. So I've chosen a topic which is, well, pretty much studied in Brazil also, which is inverse problems, in relation with another topic which is becoming more and more popular, which are degenerate parabolic equations. So the physical motivation is very simple. Although degenerate parabolic equations occur in many different applied domains, from population genetics to climate science, here I'm taking a very simple heat conduction model. So we have a conduction of heat in some body, for example, a road. And so the equation, as is well known, the equation is, well, takes into account the heat capacity, the density of the material, and also the property of the material with respect to conductivity. This is called the conductivity coefficient. Now imagine the conductivity coefficient as a failure at some point. It doesn't transmit heat as efficiently as it's supposed to be, and you don't know which point is where the crack is, and you want to find such a point. So we want to detect the points where conductivity fails. Now this can be a point, a finite number of points, or a bigger set, depending on the dimension where we consider the problem. Of course, the higher the dimension, the more interesting the problem becomes. But since we heard a lot about the curse of dimensionality, here I'm staying in dimension 1. So mathematically, we suppose to have conductivity coefficient that degenerates at some point alpha at a linear rate. So k is equal to exactly, so just to fix ideas, to this function. So it degenerates at alpha at a linear rate. So your heat equation becomes an equation like this, where in the coefficient you have exactly x minus alpha. The thing is, alpha is unknown. You want to determine such a point. Here I'm considering Dirichlet boundary condition, because I suppose that the degeneracy does not affect the boundary, and some initial condition. Okay, so the problem is to determine alpha, and also to understand what kind of measurement can be used for such a purpose. Okay, there is a huge literature on inverse problems. No point in recalling most of it. And let me just recall the book by Isakov, where in particular this kind of inverse problem, reconstruction of the conductivity coefficient, is thoroughly studied, always in the non-degenerate case for uniformly elliptic or uniformly parabolic equations. And then, well, literature on degenerate equation is also pretty large. Let me just recall a classical book by Olenik and Radkevich, and more recently, monographs by Epstein and Mazzeo, and by myself, Martinez, and Van Kostenoble, where we developed Kahneman estimates for degenerate parabolic equation in dimension 2. All the mathematics I'm going to discuss in this talk is essentially contained in this paper with Anna Dubova and Masahiro Yamamoto on the reconstruction of the degenerate conductivity region for parabolic equations. Okay, so in this talk I will briefly recall the theory of degenerate equations when degeneracy occurs at the boundary, because that was the first one to be developed, and it is also relevant to the subject of this talk. Then I will move to the degenerate equations in the interior, and after the general theory, we will see how we can tackle and solve several problems concerning the determination of the degeneracy with different kind of measurements. And finally, we'll have a conclusion open problems. So, degenerate equations at the boundary. The simplest example we can think of is an equation like this in dimension 1, where the coefficient A is positive on some interval in the interior, even in one endpoint, but vanishes in another endpoint, for example, at 0. The speed at which the coefficient vanishes determines the nature of the degeneracy, which is weak when 1 over A is a summable function, right? In this case, we can be very close to the non-degenerate case and give even a Dirichlet boundary condition on the degenerate part of the boundary. Whereas when 1 over A is not summable, the degenerate is strong, and we are not free to choose any boundary condition on the degenerate part of the boundary. But if we want to stay in L2 theory, we have to assume some kind of generalized Neumann condition at 0, where the coefficient vanishes. The natural energy spaces are defined with an H1 norm, which is weighted according to the degenerate coefficient in this way, which is very similar. I mean, the definition of the energy space, whether you are in the weakly degenerate or in the strongly degenerate case. The only difference is that functions in these spaces behave a little differently from what we are used to. For example, in the strongly degenerate case, functions of bounded energy are not necessarily essentially bounded. Nevertheless, you can introduce an unbounded operator in L2, having for domain the functions of bounded energy, for which well, the term A times the derivative is itself in H1. So as a distributional derivative, which is square summable. In this case, you define A just like the divergence of this term. And this defines a self-adjoint dissipative operator with dense domain. In the strongly degenerate case, as I recalled before, you have that elements in the domain must satisfy the generalized Neumann, homogeneous Neumann boundary condition at the degeneracy point. And so one can, by just using semi-graph theory, one can solve the initial value problem, the Cauchy problem, for a forcing term in L2, taking at 0 the degenerate part of the boundary, either classical condition like Dirichlet in the weak case, or this Neumann boundary condition in the strong case. Now that we have understood how the theory goes for boundary degenerate equation, let's see what we can do in the interior degenerate case. So here we have our equation, and I'm taking just the one I want to study. Again, we can define some energy space by requiring that this energy is finite. So these are functions which are absolutely continuous in the complement of the degeneracy point, finite energy, Dirichlet boundary condition, and you can also introduce the second order space by adding a second order weak derivative requirement with respect to the degenerate weight. So this turns out to be Hilbert space. Sorry. And again, our second order operator associated with this parabolic equation generates a strongly continuous semiconductor, this self-adjoint and dissipative. Okay, so now the problem is we know how to build solutions of this equation. How can we measure the solution in order to determine the degeneracy point? The first remark is that due to the linear decay at alpha of the coefficient, we are in the strongly degenerate case. Strongly degenerate case means that essentially there is no transmission of information from one side of the degeneracy to the other. In other terms, the problem decouples into subproblems, one to the left of the degeneracy and the other to the right of the degeneracy. These are completely independent. Of course, you have an initial condition which is defined on the interval 0,1. You take the part in the left of the left, the part to the right, and you have two problems which are independent. You can solve them independently, glue the solution together, and you get a solution on the whole interval 0,1. This means that if we want to determine alpha, we can concentrate on one of these two problems, which are problems with boundary degeneracy. So again, we go back to the initial part of the result I described. Let's focus, for example, on the second one. So we have degeneracy at alpha, then we go up to 1, and we want to reconstruct alpha from some measurement. Now, what would be the natural measurement in this case? Well, you are here between alpha and 1. Well, you can measure the solution at 1. For example, the solution at 1, the value of the solution is 0 because we have Dirichlet condition. So it is, well, natural to look at the derivative, at the normal derivative at 1. So the question becomes, now, for each alpha, I have a unique solution, u alpha, of the problem, and I have the value of the normal derivative at 1, time t. So is this map from alpha to the normal derivative monotone? That will imply uniqueness and maybe even stability of the inverse problems, of the inverse problem. Now, of course, a natural change of variable, if you start from our degenerate problem of alpha 1, problem that I am labeling P1 alpha, because it degenerates at alpha and not degenerate at 1. You change the variables in this way, you obtain another problem on 0, 1 now, which is degenerate at 0. So alpha does not appear as a degeneracy anymore, but as a coefficient. So one would think that by using reconstruction of coefficient, one could solve this problem. The problem, but that would not be enough just to consider our original problem as a detection of a coefficient, like this equation would suggest, because alpha is entering also the initial condition here. So, nevertheless, this change of variable is useful because one can still think of attacking these inverse problems by spectral techniques, trying to represent the solution after the spectral analysis of the stationary operator associated with these dynamics. So the spectral analysis will imply studying this boundary value problem, and as we know, and finding the lambdas and the phi's that solve it, the eigenvalues and the eigenfunctions. With the change of variable we saw before, the problem becomes this other one. Now we don't have an initial condition, and alpha is just a coefficient here. Moreover, more importantly, we know how to solve this problem. We can represent the solution, the eigenfunctions, in terms of the Bessel function of the first kind, J0. J0 is defined in this way, it's a well-known function, there's many applications like Bessel's function, engineering, and it has, and we are going to be particularly interested in the sequence of positive zeros of this function, J0. In fact, if we call these zeros Jn, this point here, then the eigenvalues of our problem are given by this expression in terms of the zeros of the Bessel function and of the parameter alpha. And the eigenfunctions have this representation in terms of our Bessel function of the first kind, which is composed with our transformation, with our change of variable. Jn is still the n0, and this is the absolute value of the derivative at Jn, which has an oscillating sign, the derivative. The solution, once we have the eigenvalues and eigenfunction, can be represented explicitly in this way, where now we have to compute the Fourier coefficient of the initial condition. So these u naught n are the Fourier coefficient of the initial datum u0 with respect to these eigenfunctions, after again performing some change of variables. Once you have the solution, you can compute the normal derivative at 1, just this simpler expression. Fourier coefficient, eigenvalues, zeros, and derivative of Jn. So we are going to work with this expression, trying to understand under what kind of assumptions this map depends in a monotone way, in an invertible way, on alpha, on this parameter. Alpha appears here. Okay, a first result I'm going to describe for you is how to determine alpha by a single shot, by a single time measurement of the normal derivative. This is not hard to believe because alpha is a scalar, so it is reasonable to conjecture that you can determine by a scalar. The result goes like this. Suppose the first Fourier coefficient of your initial condition does not vanish on some subinterval 0 beta. So for all alphas between 0 and beta, this is the Fourier coefficient, does not vanish. And then take two values in this interval and take the corresponding solutions of your problem. Then, for t sufficiently large, there exists t0, such that after t0, in fact, you have uniqueness of alpha, and in fact, you can bound the difference, the absolute value of the difference between the two alphas by the absolute value of the normal derivatives of the corresponding solution at time t. For all t in some compact interval, which is placed after this time t0. So you have to wait some time before the dependence becomes monotone and even strictly monotone, as this inequality says. It is interesting to stress that the constant here is uniform on the interval. So if you have an error in the measurement, you just move a little your time, that not affects the information you can derive on the alphas. And another thing is that, so we have this assumption, which is expressed in terms of Fourier coefficient. You may want something simpler, and well, a sufficient condition for this assumption to be satisfied is that the initial datum does not vanish in the interval. The initial datum here is assumed to be continuous, even Lipschitz continuous. So we expect it not to have zeros inside the interval. If that is the case, then assumption star is satisfied. Okay. So before I give you an idea of the proof, let me just show a few examples. So the result says if the initial condition does not have interior zeros, then after a sufficiently large time, dependence becomes monotone. But of course, I mean, sufficiently large time depends from case to case. For example, if I take for initial datum u0 equal 1, then sufficiently large time means any time, any positive time. For this function, you compute your normal derivative. It has this simple expression. And here is the plot of the normal derivative dependence with respect to alpha. It is monotone for any positive time in this case. And so we have Lipschitz stability for any positive time. The same thing is true for this other initial datum, 1 minus x. Again, you don't have to wait at all in order for the map to become monotone. On the other hand, I'm not reproducing all the calculation. If you take a mixture like this one, x, 1 minus x as initial datum, then you see that if time is too small, for example, time equal to 1, the dependence is not monotone. On the other hand, if you wait long enough, as the theorem establishes, the plot becomes monotone. So this is to illustrate the behavior. Just a few words. I have another 5 minutes, right? 5-10 minutes.
Yes.
Yes. Okay. Okay. So I can give you an idea of the proof and then move to other results. The proof is well, it's not hard, in fact, but again, that can be said about almost everything. So suppose, so our assumption is that the absolute value is greater than delta. So suppose the function is positive, right? Can be either positive or negative. And so this is the expression of the normal derivative. Let us differentiate this expression with respect to alpha. So when we have to differentiate the eigenvalue and the coefficient and the Fourier coefficient, we get a certain computation, which is this, which is in fact the sum of two terms. This one I'm going to call F1, and the other one I'm going to call F2. Okay, I have just factored by e to the minus the first eigenvalue, and so this is the contribution of the first term, and these are all the other terms from 2 to plus infinity. So the proof, well, consists in showing that F1 goes to plus infinity as t goes to plus infinity, and F2 goes to 0 as t goes to plus infinity. Therefore, from a certain time on, this expression is positive, and so you have strict monotonicity. You have that this function is increasing. It's increasing because we had supposed this positive. Had we supposed this negative, this would be decreasing, but still monotone, so still invertible. And then, okay, so F1 dominates over F2. Well, and this is just a matter of, well, estimates. F1 has a certain representation in terms of the first Fourier coefficient. You write explicitly what the first Fourier coefficient is and its derivative, and then you estimate. You estimate keeping in mind that this term is negative because it's the derivative of the Bessel function at this first 0, which is a negative value. And so eventually the dominant term turns out to be this, negative, this is a positive term. And since there is this t, this goes to plus infinity, as this goes to plus infinity. On the other hand, the term F2 is this term here. And the term we are, this part of the factor can be estimated in this way. Therefore, the whole term F2 is estimated by a sum from 2 to plus infinity of these exponentials, where the exponent is well negative because n starts from 2, so there is this lower bound on this difference. And therefore, again, due to this negative exponential times t, all the other terms, even the one that grow polynomially, are killed when t goes to plus infinity and the sum goes to 0. Okay, so this is essentially the first result, a single shot to determine uniquely the degeneracy. Now, what about determining not only the degeneracy, but also the initial condition? Again, well, if we want to determine both a scalar and a function on alpha 1, we may want to take a richer measurement. And here the richer measurement consists in the normal derivative not just at a point, but on a full interval. So the question becomes, can a measurement of the solution on some interval T0, T1 determine in a unique way alpha and the initial condition that now I'm calling G, just to make a difference from the previous result. And the result here goes like this. So suppose you have two Lipschitz initial datum, J1 and J2, two degeneracy points, alpha 1 and alpha 2, and the solutions of the corresponding initial value problems. Then I'm going to assume again that taking the Fourier coefficients of the initial data, J1 and J2, the first Fourier coefficient for I equal 1 and I equal 2 is different from 0 at alpha I. So these values are different from 0. Then if so this is a uniqueness result. It's not a Lipschitz stability result. It just gives uniqueness. Suppose that the measurement of the normal derivative coincides for the two solutions on some interval T1, T2, then the degeneracy points are the same and the initial conditions are the same on alpha I1. And again, this this assumption on the initial data is satisfied if, for example, the initial conditions are non-negative or have a constant sign and are not identically 0. Okay, so how much time do I have? Because I started a little earlier than I was supposed to.
I think that you have 10 minutes.
10 minutes, okay. So let me give an idea of the proof of this result. There is time to do that. Okay, so these are the representation of the normal derivatives of the first solution, of the second solution, in terms of the corresponding eigenvalues, so two different values of alpha, and two different values of the Fourier coefficient. Now, here the idea is to use analyticity. That is going to give us uniqueness, but not Lipschitz stability. The map from T to the normal derivative at 1 is analytic. Semigroup is analytic. And so, since these two functions coincide on some interval, they coincide on the whole half line from T1 on to plus infinity. So we gain the fact that this identity extends from a single interval to a whole half line. And then we will be allowed to send T to plus infinity and stuff like that. Suppose they are different, the two alphas are different. One is smaller than the other, alpha 1 is smaller than alpha 2, and then from this inequality, you deduce that the eigenvalues also respect the same order for each n. Then from this identity, we single out the first term here in the first series, and then we have all the other terms and the right-hand side. Then we divide by, we multiply by e to the lambda 1 alpha 1 t, so we divide by this factor. So the first coefficient here is singled out, then you have all the other where you have the difference, and the right-hand side where you have the difference. This is the first term, and these are all the other terms. And in fact, here you use the fact that these coefficients are all negative, because we are assuming alpha 1 less than alpha 2, and then this order of the eigenvalues, and then letting t goes to plus infinity, all these terms vanish, they go to 0, and you obtain that this guy must be 0, but we were assuming that this was not 0, and we get a contradiction. Once you have that, so there is no 2 here. Once you have that the alpha 1 is equal to alpha 2, you can prove that G1 is equal to G2, essentially by a similar argument. You use the fact that the normal derivatives are equal for t greater than t1, so you get this identity. And then you show that from this, the set of integers for which the Fourier coefficients differ must be empty. For otherwise, you could take the minimum of the set and again establish an identity by dividing by the corresponding exponential at n0. You derive an identity in which then sending t to plus infinity, you lose this part, and you recover the fact that these two terms are equal, contradicting the definition on n0, because at n0 they should be different. So this is very, very, very natural. Okay, so this is a uniqueness result with distributed measurement. And one last remark: what happens when uniqueness fails? So suppose you have the degeneracy and the initial data for which the solution of the initial value problem coincide with the normal derivative. Then, I mean, either you are in a situation where under extra assumption, ensuring the fact that alpha 1 and alpha 2 are the same, and G1 and G2, for example. You remember, we had to assume these conditions on the Fourier coefficients, otherwise they may be the same. I mean, they may be different. But what you can do, you can say, is that even if they are different, they cannot be just any values, but there must exist integers m1 and m2 such that you have this identity satisfied, where the JMs are, again, zeros of the Bessel function. So they must satisfy an equation of this kind. Of course, when they are the same, this is easy to satisfy, but even when alpha 1 is different from alpha 2, it's still constrained to satisfy an algebraic equation of this sort. And therefore, since the zeros of the Bessel function are known to be transcendental numbers, this means that the square root and the ratio between alpha 1 and alpha 2, 1 minus alpha 1 minus alpha 2, has to be transcendental. So uniqueness may fail just at certain locations. Conclusions. So the problem we have studied was to determine the degeneracy region, in this case a point, for a one-dimensional parabolic equation, which has linear decay at the degeneracy, where conductivity has a linear decay at the degeneracy. We have shown that, you can have uniqueness and Lipschitz stability for these inverse problems by a single time measurement of the normal derivative on the boundary under certain assumption on the data, if time is sufficiently large. So we have identified a class of data the one for which the first Fourier coefficient does not vanish, so on. And we have pointed out that uniqueness holds after a certain critical time for t sufficiently large. We have seen examples for which stability may fail, even for such class of data if time is too short. Then we have seen a uniqueness result for both the initial data and the degeneracy point with a distributed measurement of the normal derivative. And again, we have seen that even in this case, with distributed measurement, uniqueness may fail only at spatial locations, the ones related with the zeros of the Bessel function, so transcendental numbers. Of course, there are many open problems. This is just the first example of what one would like to study. First open problem, of course, is do not assume linear decay of conductivity, but more general decays. For example, power-like decays. You take a decay rate theta, and you put it here, and you ask the same question. Now, some things may go similarly. For example, when theta is greater than or equal to 1, but if theta is less than 1, you cannot just decouple the problem. So this makes the problem interesting, even with this modification. Another issue will be to address this problem without representation formula, without using Bessel function, getting rid of Bessel. Why so? Because, well, if we want to have any hope to study the problem in higher dimension for more general, where more general geometries present themselves, other than radial cases, you wouldn't have a Bessel function at your disposal. So maybe other tools could be used to at least confine the degeneracy region in some way. And therefore, essentially, this is the generalization that would be interesting to obtain, even in R2, in a two-dimensional domain. Suppose you have a degeneracy and, well, identify a region where degeneracy occurs, which is significantly smaller than omega, and try to get, well, uniqueness results or Lipschitz stability results for the points of this region. And with that, I think I'm finished. Let me thank my co-authors for this work, and thank you all for your attention. Thank you.
Thank you very much, Piermarco, for your wonderful talk. So now we open the turn for question comments. So if anyone has a question or comment, please just ask directly to Professor Piermarco.
Mm-hmm. Let's see if there is
okay, Piermarco, I have some curiosities.
Yes.
One is that what happens if you have in your domain 2 points which degenerate?
This has
have an operator which is x minus alpha 1 times x minus.
This is part of the extension that have to be studied. Now, with 2 points, it's maybe simpler. If the degeneracy is strong at both points. Let me go back to the. If the degeneracy is strong at both points, then you can consider the problem to the right of one point and to the left of the other point, And again, you have two separate problems with boundary degeneracy. So you have to take, of course, the normal derivatives at both extreme points, and you determine just by using this result the two degeneracy points. But if one of the points is not strong, if the degeneracy of one of the points is not strong,
yeah, but also you have, for instance, for the problem of the initial data, no? You also
no, you have, yeah, you
between the
your
two
initial data is given on the interval, let's say 0, 1.
Yes.
Then you have 2 points here,
yeah,
where if the degeneracy is linear, like here, well, you decouple your problem. You know your initial data here. You don't know your initial data here, and you determine this point by the measurement of the normal derivative at 0, and this other point by measurement of the normal derivative of 1. But so this is if you have linear decay at both points. But if the decay of the conductivity coefficient is not strong, then you are in trouble.
Yeah.
If, for example, you have weak degeneracy here, you cannot do that, right?
But
so you can
data there between the two degenerate point. Can you recover it?
No, even when we recover the initial datum in the result before, with a single point, we always recover the initial datum only here. If you want to recover the initial datum on the other side, you have to take the normal derivative also at 0.
Yes.
Okay.
So the situation is complicated, no? To recover between.
Yes. The question is complicated. This is just the first step.
Okay.
There can be several evolutions, of course. And
my second question is related that, okay, imagine that the degenerate point is not anymore fixed. It moves on time. So how to
I don't know if it moves on time. If you know the dynamics, you may try some change of variables, but otherwise, I don't know. I mean, certainly not. The Bessel function technique, as is, does not adapt to a moving alpha. And in fact, it's not reasonable to assume that you know the dynamics of alpha. Maybe you know the dynamics, not the initial condition. That's another point that one can consider. Suppose you have a degeneracy of which you know the dynamics, but not the initial condition. Well, how to determine the initial condition, in fact?
Yeah. Okay. Yeah. I have just less comment related to the case where you have two alphas, no, alpha 1 and alpha 2, because use the couple when we split the domain, no, in parts. So, for instance, in the left part that you draw that, you have some alpha minus alpha 1, let's say, but also you have a coefficient times this. So you can, I don't know if you can use
in the inequality, you mean the coefficient, you mean
yes, in the
you're talking about the Lipschitz stability result, right?
Yeah, I mean
let me go back to the Lipschitz stability result.
Can you write just an equation just to
let's see the Lipschitz stability result.
The equation is minus
this one here, right?
So the equation is ut minus alpha minus x minus alpha times.
This is to the right, or alpha minus x is if your problem lives to the left of alpha.
No, I mean, it's like a product of absolute value of x minus alpha 1 times x minus absolute value of x minus alpha 2. So
okay.
the problem one is you have a coefficient multiplying x minus alpha times some g of...
okay, you mean this, yes.
So this is difficult or not? You use a representation formula, no?
You mean?
Yes. Exactly.
Like this.
Exactly.
Equals 0. So again, I mean, locally, I mean, close to in the interval alpha 2, 1 or 0 alpha 1, it is just one of the two factors that determines the degeneracy. The other is different from 0. So in order to be able to apply this result to the situation you have in mind, you should be able to study an equation like this with a coefficient, let's say, beta of x, non-degenerate here, right?
Yeah.
Okay. Again, I don't know how to do that at the moment. We know how it goes with beta equal a constant. But in order to study this, you should be able to study it with the beta, which is uniformly positive.
No, because it depends on alpha 2, and alpha 2
yeah, but when you are on one side, no, it depends on beta here will depend on alpha 1, will be alpha 1 minus x. But when you are in the interval alpha 2, 1, this is this is a prescribed sign, right?
Okay. Just this
x minus alpha 1 should be x minus alpha 1.
Okay.
So in order to study that kind of situation, you would have to extend this result to something like this with a non-degenerate part here.
Okay. Okay, very good. Okay, thank you, Piermarco. Is there any other question or comment?
There are one question in the chat.
Sí.
Luis Yapu.
Where is
H1A,
here.
H1 alpha is immersed in L infinity in the weak case?
Yes. In the weak case, in continuous is like in the classical case, more or less, slightly different, but it still consists of continuous functions, under continuous functions. Yeah.
Okay.
Not in the strong case. Yeah.
Is there any other question or comment? If not, thank you very much, Piermarco, for your brilliant talk.
Thank you. And